It's my pleasure to introduce our speaker today, Tim Goudge, assistant professor at the Jackson School of Geosciences at the University of Texas at Austin. I don't know anything about that place, but he previous to this, he was a Jackson School Distinguished Postdoctoral Fellow, and as far as I know, and I'm pretty sure I know this right, he's the only Jackson School Postdoctoral Fellow who was then hired as faculty there. There were only like 10, but that's still a good percentage. Tim received his bachelor's degree from Queen's University in Ontario in geological engineering, as I recall, and then master's and PhD at Brown University in geological sciences. And Tim is known as basically the guy who picked where Mars 2020 is going. Obviously, there was a big process and a lot of community workshops and everything, but ultimately NASA chose to go where Tim said they should go in the beginning. So listen to what he says. And he's also taking over my lab space at UT. So without further ado, yeah, it is very messy. Glad to leave that behind. So today he's going to speak about characterizing the incision of ancient lake outlet canyons on Mars. Let's give Tim a warm welcome.
Great. Can everyone hear me with the mic? Yeah, all good? Okay. Thanks for the introduction, Jack, and thanks for having me. It's been a really fun day. A lot of really fun, well, hopefully we won't get feedback, okay. A lot of really fun meetings, hearing what everyone's up to here. It's been really great. So as Jack said, I'm going to be talking to you about ancient lake outlet canyons on Mars. Jack mentioned I was involved with the Mars 2020 landing site selection process. I'm not going to be talking about that today, but if you're interested, come talk to me after about it. I just went up to Thomas Zurbuchen and said, hey, you should go to Jezero Crater. And he was like, yeah, okay. It's not quite how it worked. But so today I'm going to be talking about outlet canyon incision. So before I start, and if this works, I'll just do the acknowledgements so that I don't forget at the end. Just want to thank some collaborators and students and postdocs and some funding sources that have enabled this work. And then also, shameless plug, I'm looking for graduate students to start next fall. So if you're an undergrad in the audience and you find anything that I talk about today interesting, come talk to me afterwards. If you don't find it interesting, you can still come talk to me afterwards. Hopefully that won't be too many people, though. Thinking about Mars and fluvial processes or water-related processes on Mars. Just starting from Mars today, we think of it as a really cold and dry environment. So average surface temperature is something like minus 60 degrees Celsius, but with major fluctuations around this average temperature. Surface pressures of something like 6 millibar, so a little under 1% that of Earth's atmospheric pressure, which is predominantly CO2. And the atmosphere is really dry. So if we take the precipitable water in the atmospheric column, so if we collapse the atmospheric column down, measure how much water we get, it's something like tens of microns of water compared to Earth's, which is very spatially variable, but of order centimeters. But modern Mars is really a very dynamic place, right? A lot of this work is being done here at LPL, showing that there's a lot going on modern Mars. But most of these are sort of dry, icy, or impact-related processes. So we have aeolian dunes moving from sediment transport, active incision in the landscape or channelized flow formation, mass wasting, impact craters excavating subsurface ice. So a lot of sort of dynamic processes on the modern surface. But if you think about what you see in the popular news about what Mars is like, in particular water on Mars, it's more like headlines like this, right? Rover finds evidence of ancient water on Mars, or headlines like this, or these, right? These headlines come up like every 6 months. This one is my favorite. Curiosity rover drills into Mars rock, finds water. The way that I imagine the Curiosity rover drills in and water just starts like gushing out of the outcrop. This is really catchy space journalism. But this evidence or indication that there used to be liquid water on the surface of Mars really goes back many decades. And there's abundant evidence for liquid water on Mars. We think it was mostly active very early in the planet's history, so before sort of 3.7 billion years ago. And we see evidence for really large incised river valleys. So this is Nergal Vallis here, which is several hundred kilometers long, a couple kilometers wide, and almost a kilometer deep. We also see evidence for fluvial sediment transport and deposition. So here's a river fan deposit that river was moving water and sediment across the landscape and deposits it in what's now a sedimentary outcrop. And then we also have Paleolakes, or ancient basins that we think held standing bodies of water. And that's what I'm going to be talking about today. And I've thought a lot about Paleolakes, that's what my PhD focused on, and I think they're really interesting parts of the landscape to study linked to this ancient fluvial activity. One of the great things about them is they tend to be large landforms, and so we can readily study them from orbit using images and topography. Those are the main data sets I'm going to be showing you today. And they provide us this evidence of interaction of surface runoff, standing water, and catching sediment in the basin interior. They can also be linked with groundwater. Some work done here showing this. From David and Jeff showing groundwater interaction with lake basins. And certainly there's a lot of people that have been thinking about this topic, so much so that it has its own textbook, Lakes on Mars, which has a lot of really good contributions to it. So there's a lot of really interesting things we can learn by studying the Paleolake record about what the early Mars surface environment was like. So this is a distribution map of all of the Paleolakes that we see across the planet, or the vast majority of them. We have over 400 of them mapped. They're shown in these black dots across Mars. They're mostly located in the southern highlands of Mars, so the younger northern plains up here, and then the older southern highlands. This is where we see most of the lake basins. And we can split these lake basins up into two different categories. Based on their hydrology. So we can think about them as hydrologically closed, and this is where we have a crater basin or some sort of basin topography, and we have evidence that water flowed into it, so an incised river valley that we know transported water into the basin, but we don't know exactly how much water ponded within the basin interior. That's contrasted with hydrologically open lakes, where we have evidence that water flowed into the basin interior. We also have a canyon draining away from the basin. So we know that water was spilling over from that basin and flowing back out onto the landscape. And so these hydrologically open lakes, this is what I'm going to be talking to you about today, and particularly thinking about the outlet canyon and how this outlet canyon might have formed. So this is an example of a Paleolake basin, a hydrologically open basin on Mars. This is the Piranha Basin. So it's almost 200 kilometers in diameter. We can see these incised inlet valleys coming into the basin here. And there's a single outlet canyon that drains away from the basin. So this slopes away from the basin here. And the only way you can form this outlet canyon is by filling this topographic low, this topographic basin, with water. So you can think about the sort of analogous idea of a bucket. If you have a bucket and you're pouring water into that with a hose, the only time you're ever going to spill out from that bucket is once you fill it up to sort of the level of the rim of the bucket or the top of the bucket. And so this outlet formation requires that you pond water in the interior, raise the lake level up to the level of this confining topography, so often defined by the sort of rim portion or degraded rim of a crater, and then the water overflows and incises this outlet canyon and connects the basin interior hydrologically with the exterior. And one of the sort of guiding ideas we have for the work I'm going to be talking about today is that this overflow flooding, it may have been catastrophic, so occurred really rapidly and done a significant amount of geomorphic work on the landscape in short periods of time. And the reason we think this is by analogy with Earth and thinking about overflow lakes on Earth. Some of the most famous examples are in the Pacific Northwest, the channeled scablands carved from the overflow of the glacially dammed Lake Missoula, as well as glacial Lake Bonneville. These carve huge canyons on the landscape as massive amounts of water are released and do significant amount of geomorphic work. So here's one of these canyons here. This is a road for scale. And I think a really great intuitive way to get a sense of the power of these floods is this picture here, which shows a sort of house-sized boulder. Here's a jeep for scale. And this is a fluvially transported boulder. So this was being moved during these floods. So huge discharges and huge velocities moving really, really large sediment. So this is in the context of thinking of an outflow flood, this is sediment, not sand grains that we normally think about, but massive boulders. And so we have this evidence for catastrophic overflow floods on Earth. There's also evidence for this on Mars, so we're not the first to sort of think about this problem. There's some really nice work by Ross Irwin in the early 2000s, who showed, based on studying the geomorphology of Madime Vallis, which is a sort of 10 to 15 kilometer, several hundred kilometer, 10 to 15 kilometer wide, almost 1,000 kilometer long valley that we see here. It flows into Gusev crater. That he showed that this was formed from the incision due to catastrophic overflow flooding from the Eridania Paleolake, which is indicated by this sort of white contour here. The Eridania Paleolake we might think of more like a sea, actually. Its volume is something like 20 times the volume of all of the Great Lakes combined. So a huge volume of water. And this filled up in this intercrater basin, filled up and then spilled over the confining topography and carved this massive feature on the landscape. But this is just one basin where this has been really looked at thoroughly, and there hasn't been much sort of systematic study of whether this process is important elsewhere. And so that's sort of what we're going to be talking about today is this process of catastrophic lake overflow flooding and canyon incision, is this common for other paleolakes on Mars? Or instead, is this incision of the outlet canyon, is this really driven by some long-term process where the valleys flowing into the basin are feeding water, and that water exits through the outlet canyon, and that outlet canyon slowly incises, slowly lowers its floor as this outflow balances inflow to the basin minus some losses from evaporation. And so we're going to test between these two end-member hypotheses. But before we sort of dive into this, it's useful to think a little bit more about this sort of conceptual end-member hypotheses we're going to be looking at. And so we're going to walk through a very simplified lake overflow scenario and talk about what the two hypotheses are. So this is a profile or cross-section through a crater, very idealized or simplified topography. We have the basin interior. We have this structurally uplifted rim, which in our case is going to act as a dam, so it's going to pond water behind it. And then we have a sloping background terrain. So the first step you need to overflow a lake, right, is to fill it up. So we're just going to do that instantaneously in our conceptual model because we get to do that with cartoon models like this. So we're filling up the basin to the level of breaching, so where it can just start to overflow this rim or the dam here. And when this happens, we know from analogy with Earth that these dam breaches, so if you have an earthen dam holding back significant amounts of water, these tend to be very catastrophic failures. And so it's likely that you're going to incise through this rim very, very quickly. But you haven't formed a canyon yet. You've formed a breach at the outlet, but you haven't formed a canyon on the landscape. So you have an exit point for the water, but you haven't formed this sort of longer canyon, this longer fluvial valley system. And so then we get into our two end-member hypotheses. So the first being that after you form this breach, you then stop the catastrophic process, and you now have normal outflow. So very slow, steady water sort of pouring over here, where the hydraulics or the hydrology is constrained by what's happening upstream in the basin. So how much water is coming into the basin, and then water has to leave to keep the mass balance here and keep the water surface elevation constant at this sort of overflowing point. The alternative hypothesis is the catastrophic one, which is that after you form this breach, you still have a lot of standing water in here. And so now you have catastrophic incision and catastrophic draining continue. And now the entire background terrain is acting as the dam. This is what's holding the water back in the basin. And so this catastrophic incision keeps happening, and that's what carves this outlet canyon. And so these are our two endmember hypotheses we're going to be testing between. And we're going to do so by looking at the geometry of the lake itself, as well as the geometry of the breach and canyon. And the reason we care about this is because these two endmember hypotheses have really distinct implications for what we might say, one, about what the outlet canyon actually tells us about the landscape evolution. So what does this canyon actually record? We also can make some interesting predictions about how the rest of the landscape might respond to the canyon incision between these two endmember hypotheses. So in hypothesis 1, where we have normal outflow carving the canyon, you would infer that the outlet canyon records something about the lifetime of the basin and the hydrology of the basin as well. So it's sort of a long-term process, recording the whole lifetime of the basin. And that in this case, the landscape, so fluvial incision sort of on the rest of the landscape, so any tributaries flowing into this canyon, are likely to keep pace because they're also driven by the regional hydrology. So regional surface runoff either from rainfall or snowmelt, depending on what your preferred conceptual model is for the climate of early Mars. In the alternative scenario, this outlet canyon only records the overflow flooding. It only records this catastrophic event and what happened in that sort of brief window of time, or however long it takes this sort of catastrophic overflow where you're not influenced by the upstream drainage. And in this case, the landscape's likely to be outpaced because we think this is a catastrophic event and is sort of removed from all of the regional hydrology of water flowing into the basin. So the talk, just a sort of brief roadmap here, we're going to discuss three main aspects all related to this problem. So first, we're going to address the problem head on. How do these outlet canyons on Mars form? Then we're going to look at whether there's ever complexities in this evolution and think about how the landscape responds. And then finally, we're going to compare Mars with Earth. So see if there's similarities or differences that we see. So this first question, addressing the problem sort of up front. So to do this, we analyzed the geometry of 24 different outlet canyons from Paleolake basins on Mars. So this again is showing the distribution in black dots of all of the hydrologically open lakes in our catalog, which is 220. And then the large white dots, these are the basins we've analyzed. These basins were picked exclusively based on available data coverage. So available HRSC or CTX DEM stereo topography. So you can see they're spread relatively evenly across the southern highlands because they're only picked based on data availability. And so we measured a couple different things, but we're really thinking about geometries and volumes all measured from topography. So the first thing we want to know is what's the amount of material that's been removed from the outlet breach and the outlet canyon. And when I talk about the outlet breach, sort of refer to just this exit point. And so for the outlet breach, we'll be thinking about what its depth is, as well as what's its cross-sectional area. So sort of how wide is it into the page. We'd also like to know the total amount of volume removed from this outlet canyon. So telling us how much erosion has gone on. So what's the entire volume of this canyon? And then we also want to know what's the volume of water that must have drained from the basin to get you to this breach point, or this current overflow point. So how much water did you have to remove, the volume of water from up here to down here to get this lake level to where it would just overflow in the modern topography? And in our two endmember hypotheses, we can think about the predictions we would make. And in our hypothesis 1, where we have normal outflow, we would predict that the eroded volume is going to be a function certainly of how much volume drained from the lake, but also what the regional hydrology is. So how much water are you resupplying to the basin that is then overflowing? and how long is that basin active? So how long is it receiving this inflow? Alternatively, in the catastrophic hypothesis, the eroded volume is only really a function of the volume drained. You're not resupplying any water to the basin really over the timescales that this incision occurs. So it's only how much water dropped to this level. And so what did we actually do? I'm going to walk you through an example. So I am walking through an example of Jezero crater. So this is Jezero, a place very near and dear to my heart. But in the context of this sort of outflow, so we're going to be looking at the outlet canyon here. It has two inlet valleys that flow in, and here's our outlet canyon, and here's the confining topography of the eroded rim. It's about a 45-kilometer diameter impact crater. So the first thing we do is map a profile from the lowest point in the basin and then out through the breach and along the outlet canyon. So this is our profile here. Here's the lowest topographic point in the basin. And if we get a profile, what we see is this. So we have elevation on the y-axis versus the distance along the profile from A to A prime. So we see we're in the basin interior here, slopes up, and here is our breach. So this is our breach point here, and then the canyon slopes down. And we can map out what we call a spillover point. And this is simply the elevation at which water would start flowing out from the basin today. So what is the level of this breach here? You can think about it also as like a drainage divide. Water on this side of this point would flow into the basin, water on this side would flow out. So this gives us the spillover point, and from that we can map a contour, which is shown in the black here. This is a contour at the elevation of the spillover point. And all of the volume below that, we can say, is water that never drained from the basin. So water from in here, when this was an active lake, it never drained from below here. All of the water was up here. So the next thing we do is look at the breach, and so I'm going to show a zoom in here. This is the breach topography. So here's the ancient rim carved through by the breach, and this is the outlet canyon here. So we map a profile across the breach. We also map the outlet canyon rims using the topography and slope maps. Here's our spillover point. And from this, we can get a profile of the breach. Here's our profile from B to B prime, and these black dots indicate the level at which the incised rim, the rim of the incised outlet canyon, intersects with this breach across the confining topography. And so to be conservative, we use this as an estimate of where the water would have overflowed. It's very difficult to recreate the exact topography when it overflowed. And so what we do is say, okay, we can see that this is an incised outlet canyon based on our slope maps. And so where this intersects with the breach, we'll use that as the proxy for the breach level. And so we can measure the depth here, the cross-sectional area. We did the same thing for profiles along the outlet canyon, interpolating between them to get a total volume of mass removed. And then we can also use these rim intersection points, as I said, to map the pre-breach water surface elevation. So at what elevation did water start flowing out before you incised this 200-meter deep breach? And from that, we can get a contour. So we now have two contours. We have our post-breach contour shown in black here, our pre-breach contour shown in white. And if we take the volume contained between them, that's the volume of water that must have drained from the basin to get the breach from what we think is the pre-breach topography down to the floor where it is now at the modern spillover point. So we know the elevation distance between these two is something like 200 meters, and we can use the modern topography to estimate what that volume is. And so what do these data look like? I'm showing you a series of three plots that look like this. This is log-log plot of breach depth on the y-axis going from 10 meters up to a kilometer. And on the x-axis here is the drained volume, again, log scale, from 10 to the 9 up to 10 to the 14 cubic meters. All of our data are plotted as gray points, and then we have this dashed power law best fit line. And so if we just look at the depth of the breach, so how deep is the outlet canyon right at the breach, we see a reasonable agreement although there's significant scatter here, and our best fit power law explains just under half of the variability in the data. But what we see is that as we add dimensions to this, so we're next going to look at the breach area. So the trend tightens up significantly, our R squared jumps up, and then finally as we look at the entire volume of the outlet canyon, so the total mass removed from the outlet canyon, it tightens up even more, and we're explaining something like 80% of the variability in the data. We're not accounting for any other type of variability that we know to be the case across Mars, so things like lithology or what the background slope is. But what we see is that drained volume to a first order seems to be a very, very good predictor of the amount of material you have eroded from the outlet canyon. And so thinking back to our predictions from our two hypotheses, we think that this strong prediction of outlet volume by drained volume is really most consistent with outlet canyon incision driven primarily by this catastrophic overflow flooding. So this hypothesis 2 that I posed at the very start. So this process that Ross Irwin also proposed for Eridania forming Madim Vallis, we think for our studied basins, this also is the dominant mechanism of outlet canyon incision. And when we think about this a little bit more, it's also kind of a bit of an intuitive finding, because what you're doing when you're filling water in this basin and ponding it behind some dam is you're really storing potential energy. So this water wants to flow downhill, and you're storing potential energy of the mass of the water in the basin. And so once it's allowed to leave and you're converting that potential energy into kinetic energy as you're moving sediment, you have a lot of stored potential energy in the basin, much more than you can generate just from the normal flow into the basin, where any flow into the basin, how much you're allowed to spill out or how much you can cause this to spill out is going to be heavily damped by the storage capacity of the basin itself. So if you have a lot of water flowing in, it's really hard to raise a lake level because that water is spread out across a large surface area. And a sort of interesting corollary, although I think one that needs to be taken with a lot of caution, is that our observations don't require any long-term outflow to explain the erosion of the outlet canyon itself. So we don't need any long-term outflow fed by inflow in the upstream portion of the basin to give us this erosion. This is very different than saying it's inconsistent with long-term outflow. So nothing in our data is inconsistent with this. All we would say is that any long-term outflow from the basin is not doing significant geomorphic work on the landscape. It's not contributing a lot to the incision of this outlet canyon. Certainly it could be contributing some, and that might describe some of the scatter in our data, thinking about what the regional hydrology is, the lifetime of the basin. But to a first order, it's not describing, or it's not contributing much of the erosion we see. There's some other interesting points about this data set that I think are cool to think about. One of them is that if you had a keen eye and were looking at our power law fit, you might notice that the exponent on the power law is very near to 1. And so we can instead fit this with a linear trend, which is a power law fit with an exponent of 1. And what we get is that the outlet volume is equal to 0.06 times the drained volume. And that's this best fit here. Doesn't fit the data quite as well, but it's really interesting to think about because what this tells us is that in a time average sense, the total amount of water that left the basin versus the total amount of sediment it removed, that ratio is something like 6%. So the bulk sediment to water volume ratio is something like 6%. When we think about rivers, even rivers that move a ton of sediment, so like the Mississippi River, the sediment to water volume ratios are much less than 1%. So this is not, and this is a time averaged signature. So when we think about instantaneously, right at the onset of flooding, when we have the most power and the water's draining the most vigorously, we might think of these things more akin to sort of a debris flow or a very sediment-saturated flow, and not necessarily like a typical fluvial system. And then as that flood wanes, it probably gets more fluvial in nature, and the amount of erosion probably drops off. And this sort of indication of the erosive power we also see in sort of qualitative sense in the basin. And this, I think, is a really cool observation, is that we actually see evidence of channelized incision on the inside of these craters. So this is the inside of Jezero, and hopefully you can see there's basically the outlet canyon extends back into the basin. This slope is uphill. And so there's so much water trying to leave this basin, and it's all leaving at this one point, so you're driving significant convergence of flow, sufficient that you can actually erode on the inside of the crater on sort of an upslope here. And this has been shown, Ross showed this in Aerodania, Neil Coleman has shown this, Wu Turmara has shown this in some physical experiments as well. So this is not necessarily a novel prediction, but something that we see that I think is really, really neat. And it's not just something we see at Jezero. We see this in a number of basins. So this is going back to Piranha here, zooming in on the outlet breach here. Here's our spillover point. And we can see this channelized incision, right? If you were mapping the outlet canyon, you might map it all the way back here, even though this is uphill. And then the sort of final point I'll make on this part of the talk is that we have this representative spatial distribution of our basins, which I showed you at the start. We also have a generally representative size distribution. So this is a cumulative frequency distribution plot, so cumulative fraction versus the post-breach volume. The thin black line here is the entire catalog of hydrologically open lakes. The thicker gray line that's more stair-stepped is our analyzed basins. And broadly, they follow the sort of same cumulative distribution curve. And so we think that these basins that we've studied, they're broadly representative in terms of their spatial distribution and in terms of their size characteristics of the entire catalog. And so, like I said, they were picked only based on data availability. And so we think that this process is probably also important for these other basins that we can't study based on just the limitations of what topographic data we have. Okay, so that's sort of the first part, thinking about how these outlet canyons form. Now that we know this, right, are there ever complexities in the system that sort of break this nice picture that I just painted? And so when we look at the details, right, are all systems so simple? Obviously the answer is no. The details are always messier. And we also want to look a little bit at how the landscape responded to these floods. So how do these tributaries that flow into the outlet canyon, how do they react when you form this massive outlet canyon? And so to look at the complexities, I'm going to talk to you about the Licus Vallis Paleolake system, which is located on the dichotomy boundary here in between sort of Hesperia Planum, the Isidis Basin, and Elysium Mons. This is Gale Crater right here, so we're a few hundred kilometers to the west of that. Here's Licus Vallis here. It's mapped in this thick black line. It's a very large canyon, so a couple hundred kilometers long. It's over 2 kilometers wide. In some places it gets as wide as 8 kilometers. It's several hundred meters deep, so minimum it's 150 meters deep. It gets up to about 400 meters deep. It terminates at the dichotomy boundary here. It has multiple tributaries that drain the surrounding landscape and join with this valley. And it also has multiple unusual geomorphic attributes about it. So this is sort of giving us a hint that it might have a more complex evolution than just a single lake overflow flood. And so the first unusual attribute of this system is that given the size of the canyon, it's fed by an unusually small paleolake. So that's shown at the upstream end here. The contour, the post-breach contour is mapped in red. This is about a 30-kilometer diameter impact crater. So it's smaller than Jezero, and it's carving an outlet canyon that's an order of magnitude larger. And so if we look at this on our plot, here is Licus if we take the volume of this small basin compared to the volume of the entire canyon. And we can see it plots sort of 2 orders of magnitude. So this is log scale, right? So we're about 2 orders of magnitude above our best fit trend, and an order of magnitude higher than the rest of the scatter in our data. And certainly, admittedly, our data has a lot of scatter in it, because it's a very simplified correlation that we've done here. But even still, we're sort of outside the bounds of that. It doesn't seem to be that it's fitting in. But it has these multiple unusual attributes, right? So maybe this is sort of explaining, well, maybe it's not just this simple. And so one of the first unusual attributes that you might have seen in that map of the outlet canyon is that we have this huge nick point right near the exit breach. So here's our exit breach here, and right downstream of that we have a massive nick point, which is a major drop in the outlet canyon floor. And so we can think of this as, Niagara Falls is perhaps the most famous nick point in the world, if not it's at least one of the most famous. Spectacular. As a Canadian, obviously I'm showing the Canadian side. The Horseshoe Falls, which are lovely. The American side, I guess, is somewhere off here. I don't know. But this Horseshoe Canyon is a major nick point. So as this river connecting Lake Erie and Lake Ontario, you can imagine its bed is at some elevation and then takes a huge drop, which is what we see here. And we know that nick points retreat. That's how they impart erosion on the landscape. And so Niagara Falls, this brink line, is actually moving upstream. It's eroding upstream. As all of this water comes over and spills over here, you're punching a pool at the bottom here, and you're removing this part of the brink line, and that drives it backwards. And there's some really, really neat mapping of the nick point retreat of Niagara Falls, some of the first work done by G.K. Gilbert, who seems to have worked on everything in terms of surface processes. So we think this nick point likely retreated up this canyon. And so if we look at the topography of this, here's a profile going from the basin interior out through the outlet canyon. So here's our spillover point here. The canyon is smoothly graded, which we expect for a fluvial system on Mars. And then you have this massive drop in topography. So it drops 200 meters over a reach of about 2 kilometers. So for context, Niagara Falls drops 50 meters, but it does so over a reach of 0. So it does so vertically. So this is not necessarily Niagara Falls, but it's the same idea. It's a very, very steep, isolated reach that we think eroded up here and then would have been abandoned at this position when this system shut off. So if we zoom out a little bit and now look at a profile of the entire Licus Vallis system, so now we're going D to D prime here from the Paleolake basin interior out through to the dichotomy boundary. Here's what we see. Here's our nick point that we were just looking at the very upstream end. And we can see that even outside of this nick point, the profile isn't smoothly graded, right? You'd be hard-pressed to fit a linear trend to the whole profile. The downstream end is certainly modified by the dichotomy boundary. So this is the dichotomy boundary here as you cross through this fretted terrain. And then there's also impact craters, so some subsequent impact craters that have ejecta into the valley that bury it. But if we just look at the there's sort of 2 linear sections of this profile. One right here, just downstream of this nick point, and then one a steeper linear section here. So if we do that, we can see this sort of slope break at about a distance of 70 kilometers downstream from the basin interior, where the slope increases by a factor of about 4. So goes from 1.4 times 10 to the minus 3 to 6.4 times 10 to the minus 3. So this is not consistent with sort of a simple canyon system or simple fluvial system that's grading one profile. And then the final thing that we see as sort of one of these unusual geomorphic attributes is that the valley downstream, in the downstream portions of the valley, we have these terraces. So this is a zoom in of Licus Vallis right here. So this in yellow here in the topography, that's sort of the background terrain, so outside the canyon rims. And then inside this, we have paired terraces, so paired flat planar surfaces. So here's one terrace on one side of the canyon wall, another on the other side here. And we see these are laterally continuous over tens of kilometers. And they define an inner valley within this broader Licus Vallis canyon. And so this inner valley is something like 2 kilometers wide and 100 meters deep. And what we put forth as our simplest and preferred hypothesis for how you would form these terraces is through 2 episodes of incision. So the first episode of incision would carve the canyon and carve it so that the floor is at the level of these terraces. So you can imagine trying to infill this valley, and that would give you the canyon at the end of the first episode of incision. If you have a second episode of incision that occurs afterwards, if water is flowing at a lower discharge or lower velocity in the canyon, you can carve an inner canyon through this second episode of incision where you carve into the previous valley floor, abandon portions of the valley floor as these terraces, and form the new inner valley floor. And so we think this records 2 primary episodes of incision. And so if we take all of these geomorphic attributes together, what we can say is that we think this is indicating an evolution that's more complex than a single episode of incision from lake overflow flooding. And so what we hypothesize actually is that there's 2 episodes of overflow flooding. One from this smaller Paleolake that's currently at the head of the valley, and one from a much broader intercrater basin that we can approximate as something like this 1,400 meter molar contour, where we don't see any valley incision actually in the basin interior currently. And this is sort of a very rough approximation of what it might have been. But you can imagine ponding water. There is a basin upstream that would have ponded water. This is no longer confined, but it constricts at the downstream end. And so you can imagine this being originally confining topography. And so the evolution we envision for this system is that first this large intercrater basin fills and overflows. That incises the downstream portion of the outlet, so our original breach point is at this slope change, and the original overflow carves this downstream portion of the canyon. Following that, you have this small Paleolake that's currently at the valley head. It fills up and overflows, and you have a second episode of overflow flooding where this overflow channel, it reoccupies the downstream portion of Licus Vallis, so it spills into that. That forms a nick point that retreats upstream, grading sort of the floor of the second outlet, and then in the downstream portion, it abandons these terraces. So we think we have sort of 2 parts of a complex system. And if we do this, we can split our data point, our anomalous data point, into 2 data points now, where the outlet volume and drain volume are much more in line with the rest of our data set. And so now we want to think a little bit about how the tributaries responded. These tributaries head at drainage divides, so we don't think there's any indication that they formed from lake overflow floods. And they record the background incision on the landscape driven by surface runoff from either precipitation or snowmelt. And so I'm going to zoom in here and show you one of the tributaries, the most upstream tributary. And what we see here is that all 4 tributaries that join Licus Vallis upstream of this slope change or upstream of our original breach point, they have major nick points in them where the tributary drops over 100 meters to the valley floor. So these tributaries are not graded to the valley floor. So it would have started as this tributary was flowing into Licus Vallis and then started retreating back from this major, very deep canyon carved by overflow flooding. And this idea of nick points in tributaries at a junction is a very common thing observed in fluvial systems on the Earth, where if you have this is an example from New Zealand, where if you have a nick point propagating up the main stem of a river valley, it can leave behind hanging tributary valleys. So if a nick point is propagating up this fluvial system, and originally the main stem and tributary valleys are graded to the same elevation, if this nick point propagates back very quickly and is now somewhere off page, if this is eroding much faster than the tributaries can erode, the tributaries will be left as hanging valleys, where they'll still have a nick point as it retreats back up and tries to grade the valley to the new main stem floor. And so if we look at the cumulative amount of retreat from the junction to when this tributary was abandoned by the main stem, we can look at, get a sense of the cumulative amount of erosion before the system shut off. And so just sort of simply thinking about this, if we assume that the main stem and the tributary valleys erode for the same amount of time, we can imagine as this nick point that once was up here at the previous breach, so the breach of the first overflow, it eroded all the way back here. So when it gets to the point of the tributary junction here, it's going to start, they're both going to start retreating away from this. So like two trains leaving from a station at the same time. But one of them is moving a lot faster. And so the main stem retreats back, the tributary valley junction retreats a little bit, and then we again hit our next tributary here, and now that's going to leave behind nick point in our second tributary valley. The main stem is going to keep retreating. And so if they shut off at the same time, if we measure the total retreat of the main stem nick point from the junction versus the tributary valley from the junction, we can get an estimate of the relative erosion rates in these two fluvial systems. This assumes the same time scale of erosion, but hopefully what I convinced you in the first part of the talk is that this is not a good assumption because we think that this lake overflow flooding is likely to be more rapid than the background incision, but it gives us a minimum estimate of by how much this main stem erosion outpaced the tributary incision. And so if we get a plot, we can plot this for our four tributary valleys that are upstream of this slope change. We have the retreat distance of the nick point in the tributary plotted from the distance between the junction and the main stem nick point. And we can see that they follow this sort of increasing trend where the tributary distance is equal to 0.3 times the main stem retreat distance. It's obviously not a perfect fit. We only have 4 data points, but generally it fits with this idea that the main stem erosion is occurring sort of 3 times faster than the tributary sort of background erosion. So we see this complex evolution of Licus Vallis, where we think we have 2 lake overflow floods, and that main stem incision is from overflow flooding is something like more than a factor of 3 greater than tributary incision. Okay, so in the last few minutes here, we're going to compare Earth and Mars. So 5 minutes to compare Earth and Mars. That's good. So when we think about these scaling relationships I showed in the first part of the talk, where we have breach depth and breach area versus drain volume, I told you also that we have a lot of overflow flooding, lakes with overflow flooding on Earth. And so we can think about whether these geometric trends, whether they scale, and whether they hold true on both Mars and Earth. And so what we've done is compare our data set with previously compiled data sets from the literature of lake basins on Earth that were breached and have outlet canyons formed by overflow flooding. And so here are the references for those databases. But we can't just compare drain volume to the eroded geometry because we want to take into account differences in planetary gravity. And so we can instead look at the potential energy that's released during the flood. And so that we can calculate as the mass of water released, so the drained volume times the density of water, multiplied by the gravitational acceleration, multiplied by the drop in the water surface elevation. So if we do this for our data set on Earth and Mars, what we see is a plot that looks like this. So breach depth, again log scale, versus potential energy released in the flood. The black or dark gray data points, those are our data points from Mars, and the light gray diamonds, those are the data from Earth. And we can see that broadly they follow very, very similar geometric scaling relationships. And the same holds when we look at breach area versus potential energy released from the flood. So these fall along a very similar power law best fit. And again, there is significant scatter in the data, but over multiple orders of magnitude in terms of the the released energy in the flood, this is a very strong predictor, the released energy in the flood, for the amount of incision. And so what we can infer from this is that when we account for differences in gravity, the main control on how much you erode the landscape is the basin size to start with, so how big is your lake that you're going to overflow, which controls this potential energy released, and then also the physics of this process, which we expect to be the same on Earth and Mars. And so this provides our strongest first-order control. And things that we have made no attempt to correct for, so things like basin shape. Is your lake in an impact crater? Is it in a glacially dammed lake? Is it in a caldera, a volcanic caldera? Anything about the basin shape has not been corrected for, nor has the eroded lithology. So are you eroding through basalt? Are you eroding through granite? These are likely providing higher order controls. So they're providing the scatter in our data set, which again is multiple orders of magnitude in terms of the erosion that you experience. But to a first order, this basin size and physics is the main control. And we think this is interesting because it might enable reconstructions of basins where you don't know the boundary conditions very confidently. So if you can measure the amount of erosion, you might be able to back out how much water drained from that lake overflow event. And so with that, I'll sort of end with my conclusions here, sort of the three parts of the talk. One, we think that Martian Paleolake outlet canyons formed during highly erosive episodes of overflow flooding. But when we look at this in more detail, there's obvious complexities. And in Licus Vallis in particular, we think there were 2 episodes of lake overflow flooding, and that the background incision is significantly outpaced by lake overflow flood incision. And then finally, that these outlet canyons, they follow the same geometric scaling relationships on both Earth and Mars, pointing to the sort of first order control of physics of the erosion as well as the basin size. And with that, I'll end and be happy to take any questions.
Yeah, you need it for the remote stuff.
Really interesting stuff, Tim. With the Licus Vallis story, it seems like there's another chapter to it in between these 2 events. You've got 2 lake overtopping events, but as you showed, it's not an enclosed basin with that larger area.
Sure.
And that's not just the canyon. On the map, you had kind of that straight line filling in. So it seems like in between the 2 events, you need a long history of erosion of some sort to move that material, which is, yet another episode of hydrologic activity on Mars that needs to be understood.
Yeah, I completely agree with you, right? So this is not closed, and we wouldn't expect it to be closed, but we would expect it to be closed everywhere except the canyon. And so, there's significant, if our hypothesis is correct, there's been significant widening of whatever the originally confining topography was. The other thing that, which I thought you were going to say is, when does this crater form? Is this crater there during the first overflow flood event, or does it form after, impact into the basin and form after, which would suggest an even more prolonged period of activity? But I completely agree with you. It's not just these 2 phases. It's much more complicated than that, but these are the 2 major phases involved in incising the main part of Licus Vallis, but there's all sorts of background landscape evolution going on and driven by fluvial processes. And trying to pin down relative rates and what the timing of this looks like, I think is a really interesting and important but difficult problem.
I'm curious, just a quick follow-up.
Yeah.
How much erosion was in that intervening event, and even just like a cross-section along that straight line?
How much do you need to widen? That's a really good question. I don't have an answer for you, but it would be pretty easy to check. I would imagine it's something like of order a few kilometers of back wasting is needed. Yeah, it's really interesting, yeah.
In terms of determining the maximum area and volume of the breach, how do you determine the end of that erosional channel?
Yeah, sure. That's a good question. I should have said that. We map it to the extent where it's no longer an incised channel in the landscape, so where it no longer has any canyon walls. And then the question is, well, what does it become? And in most cases, nothing. There's a lot of missing mass on Mars, it seems to me, right? There's a lot of evidence of incision and erosion and huge amounts of removed mass. And in most cases, it's not clear where that sediment goes. We don't see huge outwash plains of large alluvial fans at the end of these canyons. I think this is a little bit observation bias, right? It's really easy to preserve a multiple kilometer deep canyon. It's really easy to mantle a sedimentary deposit. But most cases, they just end. In some really interesting cases, they flow into another lake downstream. So Vallis is one of those. It flows into Gusev. And so you map it to the Gusev rim. But in most cases, they end their incision, or they end the present topographic expression of incision on the landscape. And so that's where we stopped mapping it.
Any other questions? I have one. I didn't, maybe you said this and I missed it, but what fraction of the Paleolake basins have these catastrophic outflow channels?
Well, so we would suggest that all of the open basin lakes, so all of the hydrologically open basin lakes experience catastrophic overflow flooding, and that's something like half of the catalog of paleolakes on Mars. And it's the majority of the catalog from early Mars's period. So we have closed basin lakes later that were active later in Mars's history, but we don't have any open basin lakes later in Mars's history. They're all concentrated earlier. So Gale Crater that MSL is exploring is a rare example of an old closed basin lake.
Lynn.
Pass it down to her.
Thanks. So yeah, this is a really cool analysis. And then I was wondering, because I know there's like Medusa Fossae formation material in this area and like possibly in Gale Crater. I was kind of wondering about the effect of having layers that are more friable and easily eroded. Like what effect that has on the erosion rate in the channel formation.
Yeah, that's a really good question. So, a major way you can form nick points is from these major lithologic variations. That's what's going on at Niagara Falls. And so if you plot up data of things that you might expect to control a nick point in a lithologically controlled environment, so watershed area or relief on the watershed, they don't give you they don't correlate with anything about how much it's eroded. So in this particular case, we don't think it's necessarily controlling the major erosion, but I certainly think in a lot of places, you see a lot of types of nick points on Mars, and I think in a lot of places they are lithologically controlled. You often see them as you erode through a crater rim, and so I think that's a major place where you might see this. And I think the Medusa Fossae, that could definitely be leading to, there's obvious signs of infill in the downstream portions of this valley or canyon that I think are potentially from Medusa Fossae, but there's any number of hypotheses for what might be giving you infill there.
Eric, get the baton. Maybe our last question before we wrap it up.
I'm sure this could be a whole can of worms to open here, but if you did have a mantled depositional fan from one of these outflows and you wanted to image it with geophysics, with seismic or radar or something, how thick could it be or expansive? Just
well, sure. We can go to our plot of the mass of material. Here we go. So this is the volume of material you're eroding. So even if you assume there's porosity involved, you're thinking order of like 10 to the 10, 10 to the 11 cubic meters of sediment that you need to deposit. And so it depends over what area you spread it out on. But if we would predict just an alluvial fan forming at the mouth of these canyons, they should be really, really thick, right? Like hundreds of meters, tens to hundreds of meters, I would anticipate. But it would be really cool. There's a lot of really simple models for deposition driven by like slope breaks. And so you could say, dump a bunch of sediment here and see how it forms a fan, and you could do a really simple test of what it might look like.
Okay, well, with that, let's wrap it up and thank Tim one more time for giving us a great
Thanks
talk.
for listening.